Today we are going to discuss the dispersive clays. Dispersive clay looks like that. Dispersive clays are highly erodible soils that have contributed to the failures of numerous earthen embankments. Dispersive clays can cause serious problems if they are not identified during the initial geologic or geotechnical investigations. If they are present but not addressed in the embankment design, they can result in structural failures. X-ray diffraction analyses have shown that dispersive clays are composed of primarily of montmorillonite, a member of smectite family of expandable clays. Most montmorillonitic clay is not dispersive, and the presence of montmorillonite alone would generally not require special treatment in structural design and construction. Dispersive clay commonly has low to medium plasticity and commonly classifies as a CL. Other USCS classifications that are sometimes dispersive include SC and CH soils. Soils classifying as MH rarely contain dispersive clay fines. Coarse-grained soils classifying as GM and GC can be affected by the presence of dispersive clay. However, when SM soils contain dispersive clay fines, they are extremely erosive. Silt-sized materials have little cohesion and are erosive by themselves. The presence of dispersive clay makes them even more susceptible to erosion. Some ML class soils composed of non-plastic to slightly plastic silts can have a low percentage of clay-sized particles and still erode rapidly under the effects of water. These soils should not be termed as dispersive clays. They are more appropriately termed silts with dispersive clay fines. Failures caused by dispersive clay fill are a result of either of the following. Number one, erosion of external soil slopes. Rain falling directly onto exposed slopes of dispersive clay can cause severe erosion. Individual clay particles become suspended in raindrops and are carried downward into the soil. Damage is severe when desiccation cracks. Desiccation cracks, the cracks which have appeared because of decrease in moisture. So I will repeat that damage is severe when desiccation cracks precede significant rainfall events, as the sides and bottom of the cracks are open and susceptible to erosion. So here you can see the actual view, erosion. Another view. Second is because of internal erosion. The most common cause of the failure of earthen embankments constructed of dispersive clay is internal erosion through cracks caused by hydraulic fracturing in the dam. Failures usually occur when the embankment is first subjected to water storage either during or immediately after construction. Failures are most common when the reservoir is filled rapidly and less frequent when the reservoirs are filled more gradually. So here you can see the actual failure because of the internal erosion. Laboratory test for dispersion. Standard soil mechanics tests such as mechanical grain size distribution analysis and Atterberg limits do not distinguish dispersive clay from ordinary clay. Color is also not a reliable indicator. A special group of tests for identifying dispersive clay has been developed. These tests are crumb test, double hydrometer test, pinhole test, and chemical test for percent sodium. So first look at the crumb test. So what we do in the crumb test, a cube of pre-molded soil approximately 15 millimeter or 5 by 8 inch on each side, about the size of a single die in a pair of dice, or a natural soil crumb of approximately similar volume is placed on the bottom of a white porcelain dish containing 250 ml of distilled water. The natural crumb must be at the natural moisture content when it was collected in the field. ASTM D6572 requires the use of a white porcelain dish. Plastic cup can also be used as a suitable replacement. The cup should have a bottom diameter of about 2 and 1 by 4 inches, a top diameter of about 3 and 1 by 2 inches, and a height of about 2 and 5 by 8 inches, and a fluid capacity of 9 fluid ounces. The bottom of the cup should have an arc about 1 by 8 inch high. Clear plastic is preferable so that any colloidal cloud reaction is visible from the sides as well as the top. Observe the crumb after at least a 6-hour waiting period and rank it according to the following system. So this is a very important point, that observe the crumb after at least a 6-hour waiting period and rank it according to the following system. So here you can see there are 4 grades: grade 1, grade 2, grade 3 and grade 4. Grade 1 means no reaction to this crumb. Grade 2, slight reaction is there. You can say some dispersion. And here the moderate reaction, more dispersion, and here severe reaction, that is the grade 4. So keep this thing in the mind that there are 4 grades: grade 1, grade 2, grade 3 and grade 4. Well, if you just look at this particular slide, here you can see the 4 grades. Again, this is the grade 1, 2, 3 and 4. So nil, slight, moderate, severe. And if you just look at these words which are written over here for non-dispersive case, nil, so you can say the water remains clear through particles. The water remains clear though particles may crumble, and the boundary of crumbs clearly defined. If you just look at this case, the slight dispersive. So here you would find these words that discoloration in surrounding particles or distinct cloudiness surrounding some. Boundary of crumbs vaguely defined. So that is the grade 2. If you look at the grade 3 case, so here you can see discoloration and cloudiness surround most of all particles. Boundary of crumbs not able to be defined. And look at the description given for the grade 4, that is the highly dispersive. And here if you just go through these words, discoloration and cloudiness surround throughout, extending vertically throughout most of all water. So these are the 4 grades. The crumb test is a good positive indicator for dispersive characteristics, but not necessarily a good negative indicator. Soils that have a grade 3 or 4 reaction in this test are almost always dispersive in other tests and in their field performance. However, soils that have a grade 1 or 2 reaction occasionally are non-dispersive in other tests or field performance, particularly in some physiographic areas. Then comes double hydrometer test. The double hydrometer test is performed in the laboratory. The test measures percent by dry weight of 0.005 mm 5 micron particles in 2 separate specimens, one of which is treated with a dispersant and the other one left in its natural condition. Refer to ASTM standard D4221 standard test method for dispersive characteristics of clay soil by the double hydrometer. So I will repeat, in the basic theme of the test is the test measures percent by dry weight of 0.005 mm particles in 2 separate specimens, one of which is treated with a dispersant or dispersing agent and the other one left in its natural condition. The double hydrometer test is not applicable to soils that have less than about 12% clay-sized particles. The test uses very small sample of soil, so with less than 12% clay particles, small errors in any measurement are magnified. If some uncertainty exists that a sample is dispersive after reviewing results of the crumb and double hydrometer test, the pinhole and chemical test can provide more information on dispersion characteristics. Well, samples must be maintained at their natural water content from the time of collection until they are tested. Once in laboratory, 2 samples of the same material are vacuum soaked in distilled water to saturation to obtain maximum dispersion. One clay sample is artificially dispersed by adding sodium hexametaphosphate and thoroughly agitating the suspension. The other sample is agitated while being vacuum soaked without addition of artificial dispersing agents. The percentage of clay-sized particles in each sample is measured using a hydrometer. Percent dispersion is defined as, so look at the formula. Percentage dispersion 0.005 millimeter, that is the percentage finer without dispersant, divided by 0.005 millimeter percentage finer with dispersant multiplied by 100. So as per ASTM, particles, the fraction that is having the particle size less than 0.005 millimeter, that is considered as clay. So this one is 0.005 millimeter percent finer without dispersion agent, divided by 0.005 millimeter percent finer with dispersion agent, and multiply this ratio by 100. So in this way you will be getting the percent dispersion. So one important point you would find on this slide: if hydrometer readings on both the treated and untreated samples produce similar clay percentages, the clay soil can be said to be naturally dispersed. The NRCS, which stands for Natural Resources Conservation Service, has developed the following general guidelines in correlating test results with field performance. So you can see that when you are having the percent dispersion less than 30, it means non-dispersive. 30 to 60, intermediate or more testing required. Greater than 60, dispersive. Then comes pinhole test. This method presents a direct and qualitative measurement of dispersibility and the consequent colloidal erodibility of clay soil by causing water to flow through a small hole punched in a soil specimen. The test method is started with distilled water flowing horizontally under a hydraulic head of 50 mm or 2 inches through a 1 mm diameter hole punched in the soil specimen. The nature of the solution emerging from the specimen under the initial 50 mm or 2 inches head provides the principal differentiation between dispersive and non-dispersive clays. Flow from dispersive clays will be distinctly dark and the hole through the specimen will enlarge rapidly with a resultant increase in the flow rate. Flow from slightly to moderate dispersive clays will be slightly dark with a constant hole size and flow rate. Flow from non-dispersive clays will be completely clear with no measurable increase in the hole size. So this is the schematic diagram. So this is for the constant head tank. It will be connected to the constant tank. Standpipe is there, and you can see that this is the soil, and a small hole has been generated through that. And over here we are having the sand or gravel. Here again we are having the sand and gravel, and from this we would be able to collect the fluid which is coming from this tube. So this is the real arrangement for the pinhole test. Test results are evaluated from the appearance of the flowing solution emerging from the specimen, the rate of flow, the final size of hole through the specimen. These observations provide the basis for classifying the soil specimen. So this slide is important because pinhole tests are rated using the following summary of criteria. So criteria are mentioned over here, and as per this slide, you can see that we are having D1, D2, ND4, ND3, ND2, and ND1. So you can go through the description. For example, we will be considering the dispersion as D1, the most severe reaction. The sample rapidly erodes at a head of 2 inches. The pinhole has enlarged to at least twice its diameter. The flow rate exceeds 1.2 milliliters per second after 5 minutes. D2, severe erosion of the hole occurs at a head of 2 inches, but up to 10 minutes is required for the flow rate to increase to more than 1 milliliter per second. The eroded hole has a diameter of 1.5 millimeters or greater. And D4, the flow rate at a 2 inches head does not exceed 1 milliliter per second, but the turbidity of the collected water is at least slightly dark. The hole diameter is less than 1.5 millimeters. At a 7-inch head, if the flow rate is more than 1.4 milliliters per second, classify as ND4. Then you would find ND3. ND3 at a 7-inch head, after 5 minutes of flow, the turbidity is at least slightly dark. The flow rate is at least 1.4 milliliters per second, and the hole diameter is greater than 1.5 millimeters. And then ND4 at a 40 inches head. If any turbidity is observed, classify as ND2. Note, not all samples are tested to a 40-inch head if evidence of failure occurs at lower heads. ND1, no erosion is observed even with 40 inches of head causing flow through the specimen. The collected water remains free of any colloidal cloud. So in this way, we can classify the dispersive clays. So here you can see the completed pinhole size measurement. So this is the hole which is present in the dispersive soil. Then comes the chemical test. A sample of pore water is extracted from a saturated slurry of a soil sample and analyzed for cations. Based on field performance, a soil's total salt content and the percentage of cations, that is sodium, are used to categorize the soil's dispersive characteristics. So percentage sodium, that is Na into 100 divided by TDS, TDS being total dissolved salt, where the TDS is calcium plus magnesium plus sodium plus K, potassium. So here you can see a plot which is needed to classify the dispersive clays. Along vertical axis we are having the percentage of sodium and sodium per TDS, and along horizontal axis we are having the total dissolved salt, and here we are having the log scale. So in this way we are having this region, zone A, then zone C is there, and then zone B. If your soil is falling somewhere in the zone A, it means it is dispersive. If it is falling zone C, it is intermediate dispersion, and non-dispersive if it is somewhere here. So you can see here some soils are marked over here: highly dispersive, moderate dispersive, slightly dispersive, non-dispersive. So basically, after plotting highly dispersive, moderate dispersive, slightly dispersive, non-dispersive soil, these zones have been developed. And you can see this particular chart on the next slide. Here it is more clear. You can see if your soil is falling somewhere here, dispersive. If your soil is falling over here, transition, and here non-dispersive. Practical considerations. The first choice is to avoid dispersive soils. Construction of earth dams would otherwise need a careful design of filter material. Next consideration is chemical treatment. That means chemical can be mixed with the soil. Lime treatment, 2 to 4% lime results in increased shear strength, reduced swell potential, no cracks induced. Aluminum sulfate, easier and cheaper to mix with soil and has much adverse effect on skin. However, it is much more expensive and has environmental effects on vegetation. And then the option of using filters containing a small percentage of fine sand silt would reduce the risk of dispersion by preventing leakage. So these are the practical considerations you can opt in the case of dispersive soils. So that's all about the dispersive soils. Thank you.